Alright guys, we want to go through the Swinburne method, and I want to take you through the formulas which you see on your formula sheet, but I'll write them down. So Swinburne method is all about how to calculate efficiency. So efficiency, every time the standard formula for efficiency, we know it as efficiency is always P out over P in times 100%. So now in this chapter for DC machines, we always deal with two machines, a generator and a motor. So then we are interested as how to calculate efficiency in a generator and efficiency in a motor. So for a generator, here's how we start. So we're still saying efficiency is still equals to P out over P in times 100%. Now the standard formula given on your formula sheet says VLIL all over VLIL plus IA squared RA plus I shunt VL plus IAO times VL, all of this times 100%. Now please be aware that efficiency, the standard does say the expression at the top is always output, the one at the bottom is always input. You apply the same principle even in this very equation here. So if you're applying the same principle in this very equation here, then in this case you're saying everything you have here at the top represents P out, everything, the whole equation at the bottom here represents P in. So if that's the case, we'll start with P out. So in this case it means P out in a generator then is represented by VLIL. Now then you will notice the formula for VLIL appears at the top and it also appears down here at the bottom. So if that's the case, we have P out at the top, we also have P out at the bottom. We can then say, considering that input power is represented by everything down here at the bottom, since the standard formula says P out over P in, whereby P in is represented by everything at the bottom, then we may say P in is equals to P out plus our different losses. So here we have these losses. We have copper losses, shunt losses, and these losses which are referred to as mechanical losses or iron and friction losses, or within the no load. So these are losses. In your textbooks they're expressed as 3 losses. So we said in this formula here, this expression here is the same as the one at the top there. So thus you have output at the top, output at the bottom. So thus, if that's the case, to fully represent the whole formula then for input power, you can also say VLIL plus IA squared RA plus I shunt VL plus IAO VL. So that's how you represent your formula for input power. The last section of this formula here, we should also know we have what is referred to as constant losses, C. C then can be represented by the part which says IAO times VL. These are referred to as ion and friction losses. They're also referred to as mechanical losses and even possibly friction and windage losses. So That's for C. Now in a motor, we are still saying in a motor now, going into efficiency, we're still saying in a motor, efficiency is still P out over P in times 100%. The given equation for a motor then says VLIL minus IA squared RA plus I shunt VL plus IAO times VL close bracket all over VLIL times 100%. In the same principle which we applied at the top for a generator, where we said everything represented at the top of this equation, into the equation for a generator, we said this at the top represents P out, the one at the bottom, everything represents P in. Same principle in regards to the same formula as well, whereby in this case everything at the top of this equation here will then represent P out, and everything at the bottom will represent P in. So if that is the case, with this one I will start with my formula for input power. So if this is the case, then it means my input power in a motor is equals to VL IL. In a generator, this same equation is expressed as output. So it's almost vice versa. Now, you will see the same trend here, where in this case, our input power VLIL is also represented there. So since we have VLIL represented here, then we can also say for our output power, P out, we have our input power minus referring to this sign, our different losses. So if that's the case, we are saying we have P in minus our losses. Your armature losses, shunt losses, constant losses, friction and iron and friction losses there. So this formula should always speak to even the one in a generator. And all I'm saying is this: if you were to notice the equation at the top, input power is equals to P out plus the losses. If you're to make input power the subject from this same equation here, then you should still get input power equals to, you transpose your losses to the other side, equals to P out plus the losses. Thus you see this formula here, this one and the one even in the motor is always the same, the equation for input power. But otherwise, we are not so much concerned as to this information I showed you. All I was saying is you will always see such a trend. They should always be the same, these two equations. Otherwise, let's move on. To represent fully the formula for output power, you can rewrite everything you have there at the top. So if that's the case, then we're saying P out equals to VLIL minus IA squared RA plus I shunt VL plus IAO VL. We are still saying C is still IAO times VL, our constant losses or mechanical losses. So there, this is the formula for efficiency in a generator and motor with the powers we have. Now, there are conditions as to how to calculate armature current. In these calculations, you will experience two armature currents. You are likely to come across two currents. The currents which you are likely to see is the current which then would be referred to as at full load, and the other current which you are likely to experience is at no load. At full load and no load, if there's anything which is the same which you may be required to calculate, is the shunt current. Shunt current, we will always say V over R shunt, same as on the no load, V over R shunt. Now, armature current, we've been calculating it since Electrotechnology N3. We calculated it at N4, Electrotechnics N4, Electrotechnics N5. For armature current at full load, we're still saying IA equals to IL. If it's a generator, you are adding. If it's a motor, you are subtracting, minus I shunt. So for full load, you just write your armature current as normal as you're typically supposed to, just IA. You don't need to be adding FL or anything. Well, that's up to you. On the no load, you are saying IAO. So we're saying IAO equals to ILO plus or minus I shunt. Plus or minus I shunt. So the formula at full load and no load are the same, except for the one on no load, we just add that 0 or O down there. So the way you will treat the equations for full load and the formulas for full load in regards to power for full load is similarly how you may treat the equations at no load, especially in a case where they happen to give you power. But the main equations which you have are the ones which we have indicated up here. So then comes this condition. So there comes a condition which is referred to then as at maximum efficiency. At maximum efficiency, we then say variable losses are equals to constant losses. Variable losses are equals to constant losses, whereby for our variable losses we have copper losses IA squared RA equals to our shunt losses plus our constant losses IAO times VL. Typically when they give us this condition at maximum, the intention for most, if not all calculations, part of the first step is for you to calculate armature current, IA. So if that's the case, then you're saying IA, you would want to make IA the subject, would be the square root of I shunt times VL plus IAO times VL all over RA, the square root of everything we have there. I've made IA the subject of the formula. So this is as far as these calculations would be concerned in regards to at maximum efficiency. Now, maybe the very last part you would want to know then is sometimes they combine these calculations with the equations for speed control. So you would then have to see, considering that I'm talking shunt, the circuit for these calculations are always shunt connected. So efficiency in a Swinburne method is always shunt connected. Shunt connected, depending on whether it's a generator or a motor, that would refer to the direction for current. But the idea is you have an armature connected in parallel with a field or a shunt resistance. There's a terminal voltage, armature resistance, and a shunt resistance. In your textbooks, this shunt is then represented as RF. What we have represented as I shunt is also represented as IF. Our armature current is still IA. The current from the supply or the line is still IL. The way I have represented these arrows, they are designed as though this would be a motor. So if it was a generator, your arrows would slightly change, especially the one for the field. So let's go into then Swinburne and speed control. So Swinburne and speed control equations. So for Swinburne and speed control, the formulas which you would need to know are the major formulas for speed control, being EMF being proportional to speed and flux, and torque being proportional to armature current and flux. If there's anything I've noticed for these calculations is that useful flux is always the same. They hardly bring cases where flux is not the same. In fact, they don't even make any comment about useful flux. So based on speed control, it would then say, if no information is given about the useful flux, then you assume that flux 1 is the same as flux 2. There's a case where they may still tell you flux is proportional to field current. If such a case is the same, as we already know, field current is the same as shunt current. Because flux would be proportional to field current, the suggestion based on this is that your field current for the original circuit would be the same as the field current for the second circuit. So this information is speed control related. So related to everything I've just mentioned here, and also if we know the two formulas being this one and this one, then to the least, if there's anything we should know, considering that flux is the same, then you say your formula E1 over E2 equals to N1 over N2. For torque, you're saying T1 over T2 equals to IA1 over IA2. So these are our main two equations. Typically, when you're given principles of speed control in a Swinburne calculation, these symbols may change depending on how they give you your information. They may decide to give you information for full load and no load. So if they give you information for full load and no load, maybe they decide to give us a speed at full load and no load. The speed at full load can still be represented as N1. At no load, it can be represented as NO. So it's just a matter of how you play around with your symbols. So please, you don't need to panic. Also, you may be required to calculate back EMF. To calculate your back or generated EMF, because these are shunt connections where the typical circuit is as the one I sketched up here. To calculate your back or generated EMF, which is around there, all you then do is you say E equals to V minus IA RA. If it's a generator, you would add. If it's a motor, you subtract. Generator, you add. So this is the standard formula for how to calculate back EMF. Principles related to armature current, we've already covered them at the top. We said in a full load, you would use this equation here, IL plus or minus I shunt. The plus sign, we need to be aware, it refers to a generator. The negative sign refers to a motor. For both sides, whether it's full load or no load, same principle under the formula for back or generated EMF. The plus sign refers to a generator. The negative sign refers to a motor. So symbols which we then need to know: VL serves as our terminal or supply voltage. We have IL. This, depending on the circuit, could be either referred to as an input or an output, but if there's anything, it is the full load. It is our full load line current. In fact, line supply or current from the supply current. They could use so much terminology even from the mains being the supply voltage side. You have IA. This is your full load. This is your full load armature current measured in amps. Your RA, this is your armature resistance measured in ohms. You have R shunt, your shunt field resistance. You have your I shunt current measured in amps. You have ILO. This is the no load current from the mains or the supply measured in amps. Then you have your IAO, your no load armature current. Your current measured in amps. What else do you need to know? We discussed C earlier on. We said these are ion and friction losses. These can also be called mechanical losses. Constant losses. We have friction and windage. We have friction and windage measured in watts. And then overall we have efficiency measured in percent. So you need to make sure you are familiar with your equations. We are about to try and answer a question. Let's do that. So let me paste one here. Alright, sorry. So for this question here, it comes from your textbooks, the exercise. So let's see if it won't beat me as well. So for this question, now before we go into the question, typically most of the given data, as long as they give you a given, like a power in a calculation, and they don't specify the given power, we always take that power as the output power. So the given power is always taken as an output as long as it's not specified. So let's approach this one. It says a 7.5 kilowatt shunt motor draws an armature current of 30 amps. So for power, P out, this is 7.5 kilowatts. It's a shunt motor. We don't need to stress the shunt because we already know all of these calculations are shunt calculations. Draws an armature current of 30 amps. So IA, we have 30 amps from a supply terminal voltage 300 volts supply. It says the shunt field and armature resistances are 200 ohms and 0.2 ohms respectively. So the first resistance is our shunt, R shunt 200 ohms. The second mentioned one, RA 0.2 ohms. Then the question says calculate the efficiency of the motor. So this is our given information. First question says calculate the efficiency of our motor. Now to calculate efficiency of our motor, we have already established that efficiency, I'll write the formula down here or maybe on the side. Efficiency equals 2P out over P in times 100%. Based on the given information, we have P out. So part of the things which we may need to consider is considering finding input power. So finding input power, maybe if you don't want to find the formula, input power, then you may consider using the whole equation for input power. Such an equation would be one where you would use the whole equation for efficiency in a motor. So the formula for efficiency in a motor, the whole formula, it says VL IL minus IA RA squared, IA squared RA plus I shunt VL plus IAO VL all over VLIL times 100%. Now, looking at this equation here, it's quite easy to find some information. Fortunately, they gave us IA squared. Well, IA, we do have RA. We have information in which can assist us to find I shunt. VL is given. But part of our challenges is we don't know how to find IAO. Looking at our data, it's not like they gave us the no load armature current or the load current. So unfortunately, this formula can't really assist us. So part of the alternative things which we may want to consider is just finding input power. So looking at the formula for input power, then the formula for input power we would consider now, this is a motor. So for our motor, let's look at the formulas we have at the top. So in a motor, input power, here's our motor. Input power says VL times IL. So if that's the case, VL times IL, let's come back here. So we're saying if input power equals to VL times IL, the idea would be we would need to find IL. Now, looking at this, they did give us armature current IA. So now, to look at IL, IL appears in the equation for IA, where you have the formula which says IA equals to, because it's a motor, you say IL minus I shunt. So then the intention would be to first find our I shunt. After we find I shunt, then we can find our IL. So to make IL the subject already from this equation here, you would say IL equals 2. You take your I shunt to the other side. So we have IA plus I shunt, and first step is to very much find I shunt. So our steps: 1. Find I shunt. 2. Find IL. 3. Find input power. 4. Find efficiency. Let's go through these steps. So if that's the case, then we have I shunt equals to V over R shunt, where we have 300 divided by 200. For this one, we are likely to get 1,5 amps. Now that we found our I shunt, we want to find IL. So originally we know the formula for IA. It says IL minus I shunt. We want to make IL the subject. So you take I shunt to the other side. You have IA plus I shunt. Now we then have 1 comma, well, our IA, they gave us 30 plus 1,5. We have 31,5 amps. Next step, find the input power. So for our input power, we are saying VL, IL, where you will have our VL, we have 300 times 1 comma, well, this is 31,5. And then let's type this. I've typed it before. 9450. 9450 watts, which can be expressed as 9,45 kilowatts. You divide it by 1,000. From there, we can calculate our efficiency. Our efficiency, we're saying it's P out over P in times 100%. Our P out was the given value we have at the top, which was 7,5. Here it is, 7,5. We have 7,5 divided by 9,45 times 100%. Then we will get how much? So we have 7,5 divided by 9,45. Then you multiply your final answer by 100. We have 79,365. 79,365%. And that's how you would go about your calculation for the first question, being looking for efficiency. So to track our steps and the marks allocated for this question, they're likely to give us 1 mark for shunt, 1 mark for IL, 1 mark for input power, 1 mark for the final answer. No marks for substitution, 4 marks. Next question says, calculate the ion friction and windage losses. So in this case, we are looking for C. So to trace our C, as we know our C is the same as what? We know C is the same as IAOVL. Now, if it's the same as IAOVL, this value here can still be represented as C in the formula for output power. So we're looking for C. So if that's the case, so since we know that IAOVL is equals to C, and we found our input power, we have the information for IA and the shunt expression, we can represent the same equation for output power, this is 3.2. We can represent then the formula for P out as VLIL minus IA squared RA plus I shunt VL plus C, where we typically have IAO VL. So we are looking for this C value here. So thus you may substitute and find the value for C. Alternatively, you could just make C the subject. I am going to substitute. In this case, my output power was given as 7, how much? I think it's 7,5. So I have 7,5 times 10 to the power 3. My VL, or this is my input power. I already found this value here. In fact, there it is. We have 9450 minus, let's use a square bracket. Our IA was given to us as 30 amps. So in here I have 30 squared. Our RA, we have 0,2, 0,2. Our I shunt, we found it earlier. We found this value at the top. Here's our I shunt, 1,5. 1,5 times our voltage. I think the given voltage was 300 volts, and we are looking for C. So we can simplify some of this information. In this case, I already have this side. I have 7,500 equals to 9450 minus, I multiply the losses I have in the bracket, 30 squared times 0,2. I have 180 plus 1,5 times 300. I have 450 plus 450 plus C. You can maybe transpose this value, take it to the other side. If that's the case, we will then have 7,500 minus 9450. We have minus 1950. Minus 1950 equals to, we have minus 180 plus 450 plus C. We can divide both sides by a negative side to get rid of this negative. Alternatively, you would be dramatic enough to just multiply this inside the bracket. The easiest way, just divide both sides with a negative sign. Eventually we'll have 1950 equals to, sorry, it's not negative again. So we have 1950 equals to, you can add these two, 180 plus 450, you have 630. 630 plus C, you transpose this value to the other side, you will get 1950 minus 630. Your value for C, we have 1320 watts. And this calculation ends here. And yeah, this is how you would go about finding your C value for this specific calculation. So the idea is, as long as we know how to use our equations for efficiency, Fortunately, like I may have mentioned at the beginning, the formulas for efficiency are given. The one in a motor being this very equation here, whereby you know everything represented at the top represents your output, at the bottom it represents your input. Same as the one for a generator, this very equation here. Same principle. So you must make sure you know how to use your equations. We want to try maybe do another question and then we will stop and move on with our lives. So this time we want to go through this one. This is a very interesting question. Typically when they give us this question, they would give you the quadratic equation as a hint. Very nice, very hot. There's a person I know, he did this question, he passed away. So poor guy. So let's try. It says a 50 kilowatt DC shunt motor running at 700 revolutions per minute. So output power, we have 50 kilowatts. It's still a motor, runs at this speed, at a speed of 750 revolutions per minute from a 500 volt at no load. So from a terminal voltage of 500 revolutions per minute, so draws 7,5, sorry, a 500 kilowatt DC shunt motor running at 700 revolutions per minute draws 7,5 amps from a 500 supply at no load. So it draws it from the 500 volt, I wrote revolutions per minute, sorry. So it draws this ILO. It draws it from the supply 7,5 amps. It says the armature, oh, we are told this is drawn at no load. It says the armature and shunt field resistances are 0,25 and 275 respectively. So they started with the armature, RA equals to 0,25 ohms. We have R shunt as 275 ohms. Okay, so let's go into the question. So the first question says, calculate the current drawn from the supply at full load. Calculate the current drawn from the supply at full load. The current drawn from the supply at full load, we are looking for IL 6.1. We're looking for IL. So in order for us to find our IL, we will then look at our information. This calculation is for 10 marks. So let's see what we can do. What we already know is that we are dealing with a motor. So seeing that we are dealing with a motor, maybe let's write the whole equation for efficiency. Then we will see what can assist us. So efficiency equals to VL IL minus, in here it's going to be IA squared RA plus I shunt VL plus IAO times VL all over our VL IL times 100%. So what we already know is that the standard for efficiency is always P out over P in. According to the formula at the bottom, we know it represents P in. So technically we have P in as VL times IL. At the top we have P out expressed as this whole equation up at the top. Based on our data, it's not like they gave us efficiency. So because they didn't give us efficiency, if we had efficiency, we would easily say efficiency equals to P out over P in times 100%. The intention would be to first find input power, where we would say P out divide by our efficiency. After we would do that, because we would have P in, we would then say VL times IL, where we would make IL the subject and say P in over VL. So we can't go about these steps I've written this side only because they did not give us efficiency. So the alternative method to go about with this one is this. So we will then notice we were given output power. We were given output power. So our output power is represented by everything up here at the top. So maybe let's write it on the side. So we're saying P out is equals to VLIL minus open bracket IA squared RA plus I shunt VL plus IAO times VL. This is our expression or equation for output power in a motor. So looking at this, based on the given data, we were given output power as 50 kilowatts just there. So this we have output power. They gave us VL. We are looking for IL. We don't have IA. We are given RA. We need to find I shunt. We are given VL. We need to find IAO. So now there's some information which VL we do have. So IAO we can find, I shunt we can find, and these two, your I shunt and IA, let's try find them first as first steps. So to find I shunt, you would say I shunt equals to V over R shunt, where you would have your V as 500 divided by, this is 275. So this is going to be 500 divided by 275. Let's check. We have 1,818. 1,818 amps. So I shunt, we found it. So we found our I shunt. Now it can help us to find IAO. We have IAO, which is going to be ILO. Because it's a mode, we're saying minus I shunt equals 2. They gave us 7,5 minus 1,818. Here we have 7,5 minus 1,818. We have how much? 5,682. We have 5,682 amps. So we now have our IAO. We now have IAO as 5, so now we have two unknowns. We are still looking for IL. We also don't have IA. So IA in a motor, it says armature current equals to IL minus I shunt. Now in this case, already you are looking for IL. When you look at the whole formula for output power, you notice you now have two unknowns. You have IL and IA. So you have two options. It's either from this equation you would want to either make IA the subject, so that later on into this same equation here, this whole equation for PL, you would either want to make IA the subject, where you will say IL minus I shunt, so that you don't have two unknowns but rather have one unknown. The alternative version would be for you to make IL the subject from this equation. So making IL the subject would be saying you take I shunt to the other side, where you will have IL equals to IA plus I shunt. And so later on, wherever you have IL into this whole equation, like such a place as this one here, if you would want, you would then substitute IL would be equals to your IA plus I shunt. then you would look for your only unknown. So in this case, I am not going to be making IL the subject. I'm going to stick to this part of this equation, whereby later on in my formula for P out, wherever I have IA, I'm going to substitute IL minus I shunt. Now, before I substitute IA, which is IL minus I shunt, I'll firstly substitute whatever I have. Now, remember, I don't have IL. So I'll write IL. Where I have I shunt, I will write 1, comma, is it 818. So let's apply what I'm talking about here, substituting IA into this whole formula. So I'll rewrite the same formula. We have P out equals to VL IL minus IA squared RA plus I shunt VL plus IAO times VL. So we're substituting our information. For P out, they gave us 50 kilowatts, which is the same as 50,000 watts, equals to our VL at the top. We have 500. Here's our 500. So we have 500 IL minus open bracket. Maybe let's use a square bracket. So it's going to be open bracket. Wherever I have IA squared, instead of writing IA, we're substituting this expression here. So we're going to have IA, it's going to be IL minus 1,818 squared times my RA value. My RA value, they gave us 0,25. 0,25 plus, let's check 0,25, this one, times, plus. Next, we have our I shunt. For I shunt, we have 1,818 times our VL, where we have 500, plus our IAO, we have 5,682 times 500. That's our C value there, this whole expression here. So from here, we want to simplify, and we are doing maths. So from here, we're saying 50,000 equals to 500 IL minus. Then we want to simplify this expression. So to simplify this expression, here's what we can do. So this part, we're going to be applying some maths. This is going to be IL minus, the whole idea is to expand, minus 1,818 into IL into minus 1,818, since the squared expression. So IL times IL is IL squared. And then for the next part, we say you would have to add these two. So I have 1,818 plus 1,818. I have how much? 3,636. So it's because these two numbers are negative. I have minus, it said how much? 3,636. 3,636 IL. Then you multiply these two at the end. So I have 1,818 times 1,818, 3,305. 3,305 plus 3,305 there. So inside these brackets here, I will have IL squared minus 3,636 IL plus 3,305 squared times 0,25. Check if I didn't do any mistakes. All right. then it's going to be plus. I can multiply these losses and those losses. So here I have 1,818 times 500. I have 909 plus we have 5,682 times 500, 2841. We have 2841 there. We continue simplifying. To keep simplifying, we have 50,000 equals to 500 IL minus, you want to get rid of this bracket. So for the first one, IL squared times this value, you'll have 0,25 IL squared minus, you multiply this value times 0,25. So we'll have 3,636 times 0,25. We have 0,909, 0,909 IL plus, this time you're saying 3,305 times 0,25. Have 0,826, 0,826. Then I'll add these two. I have 909 plus 2841. We have 3750 plus 3750. Close bracket. For our next step, we might want to just multiply this negative sign inside this bracket here. So we have 50. We are solving for IL. So 500 IL negative times this value is going to be minus 0,25 IL squared. Negative times negative, it's going to be positive 0,909 IL. These two are like terms. You can add them and multiply them by the negative sign. We'll have something like 0, this won't be 0. It's going to be 3750, 826, because I've added this value to that one. So what we did is we multiplied the sign. We said negative times positive. We got a negative sign. Negative times negative. We got a positive sign. Negative times both of these adding together. We got that. From here, you may want to add your like terms before maybe you want to transpose or make IL squared represent everything in quadratic order. So maybe let's add on the right hand side. So we still have 50, 1, 2, 3 equals 2. Arranging in quadratic order the right hand side first. So I'll have minus 0,25 IL squared. This value and that are like terms. So I have 500,909 IL minus this value here, which is 3750,826. I want to transpose everything from this side to the other side. So I'll have 0,25 IL squared. I'm taking all of these values to the left hand side. So since it was negative, it will be positive, this value. This one is positive, it's going to be negative 500,909 IL. My value has negative and it's a like term to the 50,000. So let's add these two values. So I have 50, 1, 2, 3 plus 9750,826. We're getting 53,750. So it's going to be plus 53,750, 826. Let's confirm. And so the intention or the idea of this question is to bring us to a quadratic equation. So here we are, we have IL squared, IL, and a C value. So thus we're saying IL equals to minus B plus minus the square root of B squared minus 4 AC all over 2A, where our A equals to 0.25. Our B is minus 500,909, and our C we have 53750,826. So we're substituting, we're saying IL equals to minus open bracket minus 500,909 plus minus the square root minus 505,909 squared minus 4 times our A we have 0.25 times C we have 53750,826 all over, we have 2 times 0.25. IL is equals to, let's type. So here we have minus open bracket minus 500,909 plus the square root of minus 500,909 squared minus 4 times 0.25 times 53750,826 over 2 times 0.25. So we have this very big current 1889. This is 1889, 869 amps, or IL equals to, we just change our sign, 113,766, 113,766, 113,766 amps. You will take this one as your answer for your supply current. This is a very large current here. We won't consider the very massive one. So that's how you would go about this calculation. And yeah, so maybe as time goes I might demonstrate more questions. Oh wait, let's finish this question. Let's go 6.2. So yeah, 6.2, it says calculate the full load speed of the motor. The full load speed of the motor, we've been given information on the no load. Remember it said a 50 kilowatt DC shunt motor running at 700. In fact, this is not 750. This is 700. So they gave us this speed at 700 revolutions per minute. Draw 7,5 from a 500 supply at no load. So this and that was given to us at no load. So this is at no load. You can represent the speed as NO. Someone else would represent it as maybe N2. So whichever way you represent it, the idea is it is at no load. All of the given information there. So in this case, our question says calculate the full load speed of the motor. The full load speed of the motor. So for this one, considering that they're looking for speed, you will be using your equations for speed control. So at the end of the calculation, you're going to say E or E1 over N, or N1 equals to EO, which refers to no load, over NO. So this is the given information. Remember, they did not give us any information about useful flux. Therefore, flux 1 is the same as flux 2. So this is the formula which we will be using to find our N1 or N. So in this case, we may find E or E1. To find E1, the formula for E1, since these are shunt connected, you would be saying E1 equals to V minus IA1 times RA. Or our IA1 is the armature current at full load. So fortunately, we just found our IL1 or our IL. So we're saying IA or IA1 equals to our IL1 minus I shunt. In this case, you're saying 113,766 minus our I shunt. Earlier on, we got a number such as 818. Here's our I shunt. So we have 1,818, and then you have 113,766 minus 1,818. Have 111,948. 111, how much? 948. 948 amps. So now that we found your IA1, you can find your E1. So we referred to the full load current for our IL1. Now we're saying E1, it's going to be your V minus IA1. RA, where you're saying this is going to be 500 minus 111,948. Our armature current, we had 0,25. So here we have 500 minus 111,948 times 0,25. We have 472,013. 472,013 volts. So there we found our E1. We are looking for N1. We need to find EO. This is given. We need to find EO. So this information we have is at full load. We're going to no load information. For no load, you only want to find EO. Fortunately, you found your armature current at the no load. So in this case, you just substitute. And this is 500 minus, let's check. For IAO, we found it earlier on. Our IAO is this value here, 5,682. We found this value earlier on, 5,682. So we have 5,682 times 0,25. 500 minus 5,682 times 0,25. 498, 498,57 or 58, because this 9 is affected by the 5. You just move on to the second decimal. So it's going to be 58 volts. From here, you go into the formula for speed control. You're saying E1 over E2, or rather, if you're not applying the formula like this, you're still saying EO over N1 over NO. I forgot. Based on the original formula, it says EMF is proportional to speed and flux. We did say flux 1 is the same as flux 2 only because they did not mention anything about useful flux. Therefore, originally I was supposed to write this formula as E1 over EO equals to N1 over NO, of which alternatively you can write the same equation in this manner. So remember, as we are looking for N1, so N1 then equals 2, you just cross multiply your EO, it's going to be E1 times NO over EO, where we're going to have E1, this is 472,013 times 700 all over 498,58. How much do we have? So we have, so it's 472,013 times 700 over 498,58. We have 662,7. Yeah, 662,7. 662,7 revolutions per minute, and this is our speed at full load. So for the next question, the last question. For the last question, it says calculate the maximum efficiency of the motor. The maximum efficiency of the motor. Now, for the maximum efficiency, we should be aware then that efficiency at maximum, we are required to substitute, to find our armature current at maximum. So if that's the case, you're saying the formula, you're using the formula for variable losses. You're saying that 6.3, you're saying variable losses are equals to constant losses, whereby you're saying IA squared RA equals to I shunt VL plus your constant losses. The intention is to make IA the subject, so you're saying IA equals to, let's go. So you're saying I shunt times VL plus IAO times VL all over R shunt. So when they say calculate the efficiency at maximum, always armature current and load current or supply current is required to be calculated. So the steps, typically you first go through finding your armature current, then you move on to find your IL. So here, let's substitute our I shunt. We had something like 1,818 times 500 plus, in the previous calculation, we said we had something like 5, let's check it. We had 5,682. Sorry, 5,682 times 500 all over our R shunt. They gave us something like, no, this is not R shunt, this is supposed to be armature current down here. So this is RA, which is in our case was 0,25. So let's see, we have the square root of 1,818 times 500 plus 5,682 times 500 divided by 0,25. For our armature current, we have 122,474. 122,474 amps. So now that you found your armature current, as we know, armature current is always equals to IL, since it's a motor minus I shunt. The intention is to make IL the subject. So that's you saying IA plus I shunt. You take I shunt to the other side. You need to find your new IL at maximum. So you're saying 122,474 plus 1,818. You substitute, you have 1,2 122,474 plus 1,818. We have 124,292. 124,292 amps. And from here you have your options. Part of your options are, it's either you will look for input power and output power, or you use the whole formula for efficiency. Remember, the whole formula for efficiency says VL IL over, this is the one for a generator, we want the one for a motor. So it says VL IL minus IA squared RA plus I shunt VL plus IAO VL all over VL IL. So it's either you will first find your P out, then you find your P in. Maybe let's find P out and P in. If we're going through finding P out and P in, then at the end we'll say efficiency equals to P out over P in. So we'll say P out equals to VL IL minus IA squared RA plus I shunt VL plus IAO VL. We have 500. Our new IL, we have 124,292 minus our new armature current, we have 122,474 squared times 0,25 plus I shunt, it's still the same value, times 500. Your constant losses, you're still multiplying 5, is it 628 this number here times 500. Let's substitute. This is going to be 500 times 124,292 minus open bracket open 122,474 squared times 0,25 plus, substitute these other values, we have 1,818 times 500 plus 5,628 times 500 close bracket. Let's divide by 1000. We have 54,673. 54, what? 673. 673 kilowatts. Our input power, we are saying VL IL, we're saying 500 times 124,292. So this is 500 times 124,292 divided by 1000. We have 62,146. 62,146 kilowatts. Efficiency equals to P out over P in times 100%, where we have 54,673 over 62,146 times 100. We now have, let's substitute 54,673 divided by 64,146 times 100%. We have 85,232. 85,232%. And our calculation ends here. So these are the steps you would have to go through if you came across such a question as this one. Just remember, at maximum efficiency, we always say variable losses are equals to constant losses, whereby our first step always is to find our armature current at maximum efficiency. Also, the main challenge with this question was the first part of it, where we were required to look for IL. So typically this question, when they give you 6.1, they happen to give you a hint, and that hint typically it's the, what do they call it? The quadratic equation. And so the idea is you're dealing with known and unknown values. You would notice when we approached how to check our unknown values, we had two unknown values, being IL was an unknown value and IA was an unknown value. So just around here we decided to make IL the subject of the formula to reduce having two unknown values. And so wherever we had IL, later on we substituted this. From here going downwards, we were applying maths. So typically in this calculation, you are likely to forget some of your basic maths rules, such as expansion of brackets. So such things as these, they affect your calculation, and so you happen to get it wrong. And unfortunately, because you would have maybe got the first question wrong, then you're likely to get 6.2 wrong, because the same IL value we found in 6.1 is the same value we use around there. So I hope it makes sense, and yeah. Hola.